Welcome to this explainer. If you just stop and look around you right now, the surface of the Earth probably seems pretty permanent, right? Unchanging. But it's actually this giant, dynamic canvas. Every single hill, every valley, and every coastline you've ever seen is constantly being shaped by incredibly powerful natural forces. Basically, after rocks weather and break down, it is time for nature's ultimate sculptors to go to work. So today, we're going to unpack this chapter and explore exactly how this epic story of physical geography unfolds over thousands, if not literally millions of years. Okay, let's dive into this. We're going to be meeting the four elemental sculptors that mold our world today. 1. The power of running water. 2. Groundwater's hidden caverns. 3. Glaciers, which are basically rivers of ice. And 4. Waves sculpting the coastline. Now, before we actually meet these sculptors, let's set the stage a little bit. A landform is simply a small to medium tract of the Earth's surface. If you group a few of these together, boom, you have a landscape. But here's the thing. They don't just magically appear out of nowhere. They're created by what we call geomorphic agents. That's just a fancy term for the natural forces like water, ice, and wind. And what's really fascinating here is that these agents actually take landforms through a life cycle that's kind of comparable to our own. We're talking youth, maturity, and old age. They work extremely slowly, but they completely transform the Earth's surface over vast periods of time. So, the absolutely crucial point to understand from this chapter is how these geomorphic agents actually pull this off. They rely on two core mechanical processes. On one side, we have erosion. Think of this as degradation, right? Just relentlessly chipping away at the canvas. The agent removes rock and soil, carving out deep valleys and basically scraping down mountains. On the exact opposite side of the coin, we have deposition. This is aggradation, or adding clay to the canvas, because, well, all those materials that were chipped away have to end up somewhere. They get dumped, they pile up, and they create brand new landforms. This constant, unstoppable rhythm of destruction and creation is exactly what we're going to see in every single section today. All right, let's get into it. Section 1, the power of running water, the sculptor's knife. So, in humid regions that get heavy rainfall, running water is widely considered the single most important geomorphic agent for degrading the land. It is literally nature's primary sculptor's knife, and it cuts into the earth in two very distinct ways. Take a look at the image on the left here. See those steep, almost perfectly straight sheer drops? That is a gorge. A gorge is almost exactly as wide at its top as it is at its bottom, and it typically forms in very hard rock. Now contrast that with the image on the right. That's a canyon. Look at those wide step-like side slopes. A canyon is much wider at the top than at the bottom, and it usually forms in horizontally bedded sedimentary rocks. But you know what's crazy? Both of these massive valleys start as tiny little rills of water that deepen into gullies, and eventually, just through the sheer friction of flowing water, they become these massive formations. But what happens when that rushing river finally slows down? Well, when streams reach gentler slopes, they stop cutting downward quite as much and actually start eroding sideways. This creates those beautiful, sinuous curves called meanders. Here's how it plays out step by step. The water flows and hits the outer concave bank, constantly eroding it away. But at the exact same time, the slower water on the inner convex bank is doing the opposite, depositing sediments. Over time, this loop gets so extreme that the river just decides to cut right through the inflection point. It takes a shortcut, leaving behind this isolated crescent-shaped body of water that we call an oxbow lake. It's just erosion and deposition working in perfect harmony. Now, think about what happens when a river overflows. The sculpting doesn't stop, it just changes. Floodwaters spill right over the banks, dropping their heavy sediments to build up a wide, flat area called a floodplain. If you look closely at the edges of the river here, those linear, parallel ridges of coarse deposits running right along the banks, those are natural levees. And on the inside curves, you can clearly see point bars forming from all those deposited sediments. So, just to quickly wrap up running water, try to remember your key erosional features from the chapter: V-shaped valleys, deep plunge pools, and step-like terraces. But remember, as slopes gently level out, deposition takes over the show. That's when you get alluvial fans at the base of mountains, deltas where the rivers finally meet the sea, and those vast floodplains. Eventually, given enough time, running water will flatten absolutely everything into a low-relief plain called a peneplain. Moving right along to Section 2, Groundwater's hidden caverns, the chemical artist. Leaving the surface behind, we find that groundwater doesn't really work through brute physical force or rapid flow. No, it's more of a stealthy chemical artist. And this chemical artistry really only works on very specific canvases, namely calcium-rich rocks like limestone and dolomite. When surface water percolates down through the little cracks and joints of these rocks, it literally dissolves them away through chemical solution and precipitation. This specific type of highly unique landscape, carved almost entirely by dissolving rock beneath our feet, is called karst topography. Let's take a quick tour underground, shall we? Up at the surface, the water eats away at the limestone to create these big funnel-shaped depressions called sinkholes, and sometimes these collapse right into empty, dark voids below. If you journey down past those sinkholes, you enter the cave system itself. Inside these caves, calcium carbonate precipitates right out of the dripping water. Look at the top of the cave there. Stalactites hanging down just like stone icicles. Now look down at the floor. Stalagmites rising upward to meet them. When a stalactite and a stalagmite finally connect, they form a solid pillar. It's wild to think about how long that actually takes. To summarize our groundwater vocabulary, your erosional features are all about things dissolving. Sinkholes, which are also called dolines. If a bunch of sinkholes merge together, they form these long trenches called uvulas. And those extremely irregular, jaggedly grooved surface ridges they leave behind, those are called lapes. And hey, a quick word of warning here. Sinkholes are quite often covered by a shallow mantle of soil and just look like simple, innocent water pools. If you aren't careful in a karst landscape, you could step right in and drop down just like in quicksand. As for the depositional side, well, that's entirely inside the caves. Your hanging stalactites, your rising stalagmites, and those solid pillars. Next up is Section 3, Glaciers, Rivers of Ice. Think of this one as the heavy bulldozer. Shifting gears completely from delicate chemistry, we have the massive, slow-moving, crushing power of glaciers. Glaciers are literally rivers of ice. They flow down mountain slopes or spread out across flat plains entirely because of gravity. Erosion by glaciers is tremendous, simply because of the immense friction caused by the sheer weight of the ice. As this colossal heavy mass moves, it drags large, angular boulders along its floor and along its sides. This process of abrasion and plucking is so deeply destructive that it can literally reduce high mountains into low hills and carve out these massive, distinctive U-shaped valleys. Take a look at the aftermath of this bulldozer right here. When the ice finally melts and retreats, it just unceremoniously dumps everything it was carrying. This unassorted, coarse debris, which we call glacial till, piles up into these long, continuous ridges known as moraines. But you'll also notice these weirdly smooth, oval-shaped hills scattered all around the landscape. These are called drumlins. And when meltwater streams flow beneath the ice sheet itself, they leave behind long, winding, snake-like ridges of coarse boulders known as eskers. To summarize these glacial landforms, just remember that the erosional features are incredibly sharp and jagged. You've got cirques, which are deep, bowl-shaped basins cut right into the mountaintop. When a few of those cirques erode headward towards each other, they create these incredibly sharp, pointed peaks called horns. In fact, the Matterhorn in the Alps and even parts of Mount Everest are actually horns formed by this exact type of glacial erosion. Depositional features, on the other hand, are way smoother and mostly made of that dumped till we talked about, like your moraines, flat outwash plains, and those oval drumlins. And finally, Section 4, Waves Sculpting the Coastline, the Relentless Pounder. While glaciers take thousands and thousands of years to do their thing, our final sculptor works on a highly dynamic, rapid, and often destructive timeline. When we look at coastal evolution in this chapter, we divide the world into two main types of coasts. First up, high rocky coasts. These are submerged coasts, and they are completely dominated by destructive wave erosion. The hillsides just drop off sharply right into the water. Conversely, we have low sedimentary coasts. These are emerged coasts, and they're dominated by steady sediment deposition, where rivers slowly build plains and deltas out into the sea. For a great real-world example, the west coast of India is a high, rocky, retreating coast, while the east coast of India is a low, sedimentary, depositional coast. Now, on those high, rocky coasts, destruction happens in a really fascinating, sequential way. First, the waves just relentlessly pound the base of a steep sea cliff, eventually hollowing out a sea cave. Next, over time, the roof of that cave simply cannot support itself and it collapses. The cliff recedes inland, leaving behind these isolated, stubborn rock pillars standing out in the water, which are called sea stacks. But the waves don't stop. Eventually, even those resilient sea stacks erode away completely, leaving behind nothing but a narrow coastal plain. So, to recap this rapid coastal destruction and creation,
The relentless pounding leaves us with erosional sea cliffs, sea caves, and those temporary sea stacks. But remember, all those broken down rock fragments eventually roll around, get grounded down to roundness, and build our absolute favorite depositional features, beaches. Longshore currents also build up these submerged sand ridges called bars. When those bars manage to rise above the water level, they become barrier bars, which can actually enclose bays to create calm lagoons. Given enough time, and those lagoons will fill entirely with sediments and become part of a broad coastal plain.
Wow, we have covered a massive amount of ground today, exploring exactly how the Earth's surface is constantly being destroyed and reborn. We've seen the carving knife of running water, the totally stealthy chemical magic of groundwater, the heavy bulldozer of slow-moving glaciers, and the relentless pounding of ocean waves. So I'm going to leave you with this. Take a second and look out your window. What geomorphic agent is shaping your own neighborhood right at this very moment? Is it running water, wind, and more importantly, what on earth is your landscape going to look like in a million years? Thanks so much for exploring this chapter with me today.